Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as EMI. Let's start with impedance. Now, what do we understand by impedance? Practically in an AC circuit, there are three circuit elements: the resistor, the inductor and the capacitor. Now the resistor opposes the flow of current due to resistance. The inductor and the capacitor oppose the flow of AC current due to inductive and capacitive reactance. Resistance does not depend upon the frequency of AC, but the inductive reactance and the capacitive reactance depends upon the frequency of AC. This combined opposition to the flow of current is called as impedance. That is the opposition to the flow of current due to resistance, capacitive reactance and inductive reactance. This combined opposition is called as impedance. Right? I can say that AC circuits consist of three circuit elements. That is resistors, inductor and capacitor. Right? A resistor opposes the flow of current. A resistor opposes the flow of current due to its resistance. The inductor and capacitor oppose the flow of AC current. Due to their inductive and capacitive reactance. Right? Our resistance is independent. The resistance is independent of the frequency of AC. However, the inductive reactance and the capacitive reactance depend upon the frequency of AC. Right? The combined opposition of all these to the flow of AC current, is called impedance. Right? Impedance is denoted as Z. Now, let's try to find out what is the value of Z in an AC circuit. Right? Now, the quantity Z plays the same role in an AC circuit that the quantity R plays in a DC circuit. I can say that the quantity Z plays the same role in AC circuit that quantity R plays in DC circuit. Fine, do we get this thing here? Now, if let's consider the different types of AC circuit, right? Consider the following cases of AC circuit. First, let's consider if there's only R and L in the circuit. If resistance and inductance are connected in series. If R and L are connected in series. Now, if R and L are connected in series with EMF source, then in that case I can say that the impedance in the circuit Z. Now we know that resistance is going to be in phase with the current, and we know that there is a phase difference of 90 degree between the current and the EMF. Thus I can say that resistance and the impedance are going to have a phase difference of 90 degree, and since they have a phase difference of 90 degree, they can be solved by using Pythagoras theorem. So if I use Pythagoras theorem, then I can say that impedance is equal to R square plus XL square, but XL is equal to 2 pi FL, so this is going to be R square plus 2 pi FL the whole square. This is going to be the impedance in a series circuit with R and L, right? Do we get this thing clear? Next, let's consider another case. If resistance and capacitance are connected in series, if R and C are connected in series with the EMF source, then I can say that the impedance in the circuit Z is going to be, again we know that capacitive reactance and the current are 90 degree out of phase. Now in that, and resistance is in phase with the current, therefore there will be a 90 degree phase difference between the resistor and the capacitive reactance. Hence I can solve this again by using Pythagoras theorem. So I can say Z is equal to R square plus XC square, but XC we know is nothing but 1 upon 2 pi FC. So I can say R square plus 1 upon 2 pi FC the whole square. This is going to be my impedance in a circuit with R and C. Next, if I have resistance, inductance and capacitance in series, if R, L and C are connected in series, with the source, with the EMF source. Now, in that case, the impedance in the circuit Z is going to be equal to square root of R square plus XL minus XC whole square, right? Now I can say that this is going to be equal to square root of R square plus omega L minus 1 upon omega C the whole square, right? This can be written as square root of R square plus 2 pi FL minus 1 upon 2 pi FC the whole square. That is going to be that will be the impedance in an LCR circuit. Now, if E0 and I0 denote the peak value of EMF and current, if E0 and I0 denote the peak value of EMF and current and ERMS and IRMS denote the RMS value of EMF and current. Then I can say that you can say that the impedance in the circuit is EMF, peak EMF upon peak current, or it is also equal to RMS EMF upon RMS current. Right? Thus, how do I define impedance? I can say thus, impedance in an AC circuit is the effective opposition opposition offered by the circuit to the flow of AC current. Right? So impedance is the opposition that is going to be offered by the circuit to the flow of AC current. Right? And how do I define this? Definition wise, I can say it is defined as the ratio of RMS value of alternating EMF across the circuit, to the RMS value of alternating current in the circuit. Right? That's how I define impedance. Next, let's find out the power in an AC circuit. Right? Let's consider an AC circuit in which resistance is connected. Right? Consider first case. Consider an AC circuit with resistance only. Right? So let's draw an AC circuit with just resistance in that circuit, EMF, and you have resistance. This is EMF, this is resistance R. So I'll say consider an alternating EMF applied across a resistance R. Right? Now I can say that in this circuit the EMF and the current will always be in phase with each other. The EMF and current will be in phase with each other. The instantaneous EMF E can be written as E0 sin omega t. That will be the instantaneous EMF, and the instantaneous current in this circuit I is going to be nothing but I0 sin omega t. Right? Now in this case we know that power in a circuit, the instantaneous power P, power is defined as the product of EMF and current. Power is defined as the product of EMF and current. So in that case this is going to be E0 sin omega t into I0 sin omega t. Right? So in that case I can say this is nothing but E0 into I0 sin square omega t. Fine, do we get this thing clear? Now since E and I are changing, the power will also change. Since E and I are constantly changing, therefore the instantaneous power will also change. Right? Now if the instantaneous power is going to change, let's find out the average power. Let PAV be the average power in one complete cycle. Right? If this is the average power, and if the instantaneous power is assumed to be constant for a very small interval of time dt, consider that the instantaneous power is constant for a very infinitely small interval of time. Interval of time dt. P is the power and the power is constant for a very small interval of time. Then the work done in one complete cycle, what will be the work done in one complete cycle? The work done in one complete cycle is going to be nothing but the integral of power and time, right? P dt from 0 to t, where t is the time period for one complete cycle, where t is time for one cycle. Guys, how did I get this? We know that power is work upon time. That's how I got work is power into time. That's how I got that equation. And we assume power to be P and time to be dt, right? In that case, I can say therefore the average power will be the work done in one cycle divided by the time for one cycle. Work done in one cycle upon time for one cycle. That is going to be the average power in the circuit. Now, work done for one cycle we have already found out as integral of 0 to t p dt. So P average is integral of 0 to t p dt upon time for one cycle is t. So this is going to be 1 upon t integral of 0 to t. But power, P instantaneous power we found out is nothing but E0 I0 sin square omega t dt. The value of instantaneous power was E0 I0 sin square omega t. Now, where E0 I0 are constants, so I can say this is E0 I0 upon t integral of 0 to t sine square omega t dt, right? But omega is nothing but 2 pi upon t, right? So in that case I can say that, but you can say it can be proved that integral of 0 to t sine square omega t dt is nothing but t by 2. Right? You don't have this derivation, you have to know this, that sine square omega t dt is nothing but t by 2. Now substitute this value. In that case I can therefore say that average power is E0 I0 upon t into t by 2, right? So in that case I can therefore say that P average is E0 I0 upon 2, but 2 can be written as root 2 into root 2, so that's E0 upon root 2 into I0 upon root 2, but E0 upon root 2 is nothing but RMS EMF, so P average is E into I. So the average power in the circuit is RMS value of EMF into RMS value of current, right? So I can therefore say, therefore the average power dissipated in a circuit, the average power dissipated in an AC circuit, containing resistance only resistance only is given by the product of effective voltage and effective current. That's the average power in a circuit containing resistance only. Now, let's find out the average power in a circuit containing inductance only. Consider an AC circuit with inductance only. Let's draw an AC circuit with inductance only. E I L, right? Now, so in the case of an AC circuit, containing inductor only, I can say that the EMF leads the current by pi by 2 radians. EMF leads current by pi by 2 radians, right? Now the instantaneous current, the instantaneous EMF, E for an inductor circuit is given by the formula E0 sine omega t plus pi by 2, right? And the instantaneous current I is going to be nothing but I0 sine omega t, right? Now once you have this, let's find out the instantaneous power. The instantaneous power is defined as the product of EMF and current. So this is going to be nothing but E0 sine omega t plus pi by 2 into I0 sine omega t, right? This is going to be nothing but E0 I0 sine pi by 2 plus theta. Sine pi by 2 plus theta is equal to cos theta. So this is going to be cos omega t into sine omega t, right? So that is going to be the instantaneous power in the circuit. Once you have this, let's find out for one complete cycle what will be the average power. I can say over one complete cycle. Over one complete cycle, I can say that the average value of sine omega t cos omega t is going to be equal to 0. For one complete cycle, the average value of sine omega t plus cos omega t is going to be equal to 0. So that means I can therefore say that integral of 0 to t sine omega t cos omega t is dt is equal to 0, right? Thus I can say that the average power in the circuit is nothing but 1 upon t integral of 0 to t p dt. That's the formula for average power in the circuit. Now p value can be substituted as this is, I can say that P average is 1 upon T integral of 0 to T E0 I0 sine omega T cos omega T dt, right? Now this can be written as E0 I0 upon T integral of 0 to T sine omega T cos omega T dt. But we already said that the value of integral of sine omega t cos omega t is 0. So this is going to be 0. So the average power in a circuit with only inductance is going to be 0. Fine, do we get this thing here? So I can say that hence the average power absorbed by a pure inductor is 0, right? Now during one cycle the average power absorbed by the whole inductor is going to be equal to 0. Next, let's see an AC circuit with capacitor only. Consider an AC circuit with capacitance only. Right? Same thing that we've been doing. Consider a circuit with capacitance only. AC source, EMF, current, capacitance. Right? So I can say in the case of an AC circuit, with capacitance only. Now in the case of capacitance, we know that the EMF lags the current by pi by 2. EMF lags current by pi by 2 radians, right? So in which case therefore I can say that EMF, instantaneous EMF, the instantaneous EMF E can be written as E is equal to E0 sine omega t minus pi by 2, since it lags the current, right? And I, the instantaneous current, is going to be equal to I0 sine omega t. Right? Now, the instantaneous power in the circuit P is going to be product of EMF into current. So this is going to be nothing but E0 sine omega t minus pi by 2 into I0 sine omega t. Right? Now, this can be written as, if I take minus sign common, see this is E0 I0 as it is, sine, take minus sign common, so minus pi by 2 minus omega t into sine omega t. Sine of minus theta is minus sine theta, so the minus sign comes out. Sine pi by 2 plus theta is cos theta, cos omega t sine omega t. Right, so the instantaneous power will be minus E0 I0 cos omega t sine omega t. But over one complete cycle, the average value, the average value of sine omega t into cos omega t is 0, right? In which case I can therefore say that integral of 0 to t sine omega t cos omega t dt is 0, right? Now let's find out the average power. Average power is 1 upon t integral of 0 to t p dt, 1 upon t integral of 0 to t minus E0 I0 sine omega t cos omega t dt, right? Your minus E0 I0 constant comes out upon t integral of 0 to t sine omega t cos omega t dt, but sine omega t cos omega t is equal to 0, so this is minus E0 I0 upon t into 0, which is 0. Thus the average power in a consumed by a pure capacitor is 0. Therefore I can say that average power consumed by pure capacitor is 0. So now we know what is going to be the power in a resistance only circuit, an inductance only circuit, a capacitance only circuit. Right? Now let us try to mix them and get different combination. We will do that in the next lecture. We will stop this here for the day. Thank you very much.